much, Irina, for the invitation. I'm very happy to be able to present in this audience today since, yeah, as we just mentioned, we have extended our droplet injector applications to synchrotron sources lately. And so I will talk about crystallography. A big part of my talk will be on X-Files, but then at the very end, I will go into our latest approaches that we have attempted at the ESRF synchrotron. So I'm a professor in the School of Molecular Sciences and the Center for Applied Structural Discovery at the Biodesign Institute, and both are located at Arizona State University. Okay, so my slide is not advancing and Zoom tells me something. Okay. Oh, dang it. I need to approve something and it doesn't let me go there. Here we go. Okay, good. So I wanted to start this presentation with a short discussion about sample consumption in crystallography. And we can hypothesize about what would be an ideal sample consumption. So let's assume we have a microcrystal of 4 by 4 by 4 micrometers and a smallish protein in the range of a few tens of kilodalton, then that would amount to about 50 picogram of protein. As we know in crystallography, we get fraction patterns from one crystal that we then merge together, and we need about 10,000 hits or so that are indexable to get a structure. So that brings us to about 500 nanograms of protein that is needed to obtain a structure. Now, in terms of sample delivery, we have several approaches to bring sample into the path of an X-ray beam. And here I wanted to point out how much sample and in terms of volume then we would need in order to achieve, these 10,000 hits. So with a fixed target device, we could imagine that we spread out these crystals in a 100 by 100 array and that they're located about 25 micrometers apart. Let's then assume that our fixed target device would be just a little bit larger than the crystal, so about 5 microliters, and translating that in a volume would give us about 30 nanoliters. Taking the 10,000 crystals that we would need into account, then we end up with a crystal density of about 10 to the 8 to 10 to the 9 crystals per milliliter. And if we look at liquid injections, then one of the still very commonly used injection methods is a continuous injection with the so-called gas dynamic virtual nozzle. And then we can do calculations dependent on the X-Fill source we use. So, for example, 120 hertz, which would relate to LCLS, we would need tens of microliters in a crystal density of 10 to the 10 crystals per milliliter, just assuming that each crystal will be hit by the X-Fill, and that we need a certain amount of liquid to inject these crystals in a jet. At the European X-Fill, the ideal sample consumption would then be just a few microliters with a lower crystal density. That's assuming that we have these pulse trains that have megahertz-spaced pulses, about 350 or so currently at the European X-Fill. We can also look at droplet injection, which is probably out of the three that I provided here, the one with the lowest sample consumption. So if you assume that you can keep your crystal into a 5 micrometer diameter droplet, and each of the droplets containing one crystals would be hit by an X-ray laser, then you end up with about 650 picoliters needed. If you put your 10,000 crystals into one such droplet, then you would have a crystal density of about 10 to the 10 crystals per milliliter. So this is all hypothetical because as we see, when we look at what people have been reported about crystallography and sample consumption, we can see that the picture is orders of magnitude away. So in this in this representation, you actually see different injection methods, the liquid injection methods, both containing the GDVN and the viscous injectors, hybrid injections, and then also the fixed target ones realized in different materials. You can actually see all of them are orders of magnitude away from this ideal sample consumption. And probably the fixed target methods are doing the best here. Anyways, as I mentioned, one of the still very commonly used methods to bring crystals into the path of an exfil beam is liquid injection with our gas dynamic virtual nozzle. And that's depicted in this schematic. So basically, we use a nozzle that jets a thin jet of the crystal suspension into the path of an X-ray beam. And then if the crystal happens to be in the interaction region, it's hit by the exfil pulse and then provides a diffraction pattern. And this method has been very successfully used to determine structures of membrane proteins, and it has also been used in time-resolved crystallography, both light-induced and chemically induced for enzyme reactions, for example. So it is still a very popular method, and as we have seen, the sample consumption rates are particularly high for these GDVN methods. So we have been working on attacking this issue and contributing to reducing the amount of sample used in zero crystallography with liquid injection with a droplet approach. So it remains sample consumption remains a major challenge. And the proposition that we have made a few years ago was to segment crystals in droplets separated through an immiscible oil, and then shown in this slide. It's contrasted with the continuous injection, and you see, and anytime the laser is on, we would basically waste material in these experiments. However, if we can deliver crystals in droplets only when the exfil pulses, then we would reduce the sample consumption significantly. And so what we would like to achieve is, instead of needing hundreds of milligrams of protein to obtain a structure, we would like to decrease that to below 10 milligrams. I brought also a schematics about the European exfil with its unique pulse structure, just to demonstrate that we would then aim for injecting one droplet per pulse train. So we would cover the full 300 or so pulses, megahertz pulses in a pulse train to cover with the droplet. Okay, so this is what we'd like to do. We would like to generate droplets. We would keep the capabilities of the GDVNs and the jetting capabilities, and then synchronize the arrival of the droplets with the exfil pulses. That's contrasted again here in the schematic. So on the top with the continuous injection and the GDVN, and on the bottom with our segmented droplet approach. As you see, we're generating droplets in a microfluidic device, and then we jet them through the nozzle, where the droplet will be thinned out into a microjet, and crystals are intersected with the X-ray beam in that microjet once they left the nozzle. So we've done some calculations based on achievable droplet sizes and jet speeds. And so you can see that on all currently available exfils, we get to larger than 90% sample savings with a certain droplet size assumed here. And in this case, about 500 picoliters droplet size and a jet speed of 30 meters per second. One of the instruments that would probably benefit the most is the European exfil due to its unique pulse structure. And I've showed you that we want to cover the megahertz repetition at pulses with our droplets. And I put here also synchrotrons with a question mark. So we have, as I mentioned in the beginning, started applying these droplet injectors also for synchrotron zero crystallography experiments. And we have some data that I will show at the end of my talk from ESRF at ID29. Okay, so the gas dynamic virtual nozzle, I brought a slide to explain how it works. So basically, it's a capillary in a capillary. So we deliver the crystal slurry in an inner capillary that will be surrounded by gas through an orifice and then creating a jet. The jet eventually breaks up into droplets, but that's not the region that we're interested in intersecting it. So we want to keep it in the range where it's still a continuous jet. The first realizations of these gas dynamic virtual nozzles were quite cumbersome and tedious to make. They were actually really made out of a capillary that had to be mounted in another capillary, grinded and pulled, and it was a quite time-consuming work to do this and required people that were specially trained to do that. With the advances of 3D printing, I believe the field now moved entirely to printing these nozzles. The high resolution printers are capable of achieving similar capabilities. And what you see here is a 3D printed piece that is attached through fused silica capillaries now by gluing it together, basically. And these nozzles have been very successfully used as well for zero crystallography. Now, we wanted to keep this capability of 3D printing and combine it with droplet generation. So basically, we developed a microfluidic droplet injector that is realized by two channels that meet at an intersection. One channel will carry the aqueous sample solution or suspension, and the other one will carry the oil phase. At the intersection, the droplet is sheared off. And that's not at all a novel concept in microfluidics, so that has been practiced for quite a while. And we combine it with these high-resolution 3D printing and through two-photon polymerization. So our first realization of a droplet generator was a simple T, but the video basically shows that this is working nicely. So this is just water in an oil phase, and the principle in general functions. So in order to actually integrate it for a sterile crystallography experiment, our droplet generator needs to be compatible with a few other things here, and we had to develop some diagnostics as well for the generated droplets. Keep in mind that typically these experiments are carried out in vacuum, so everything needs to be vacuum compatible. The crystal slurries are typically pumped through a sample reservoir that is shaken during the experiment, so crystals do not settle, and the flow is initiated through HPLC pumps. So we can realize the same for the oil that we need to generate the segmented droplets. We integrate flow sensors to understand the flow rates. Then we have our droplet generator generating the droplets, which are then downstream detected by a droplet detector. We have designed these droplet detectors to be compatible with vacuum insertion. So it's a fiber optic custom-made assembly using infrared light to detect the oil phase and the aqueous phase, and a typical droplet signal you see here in the schematics. So that allows us to diagnose the frequency, but it allows us also, as I will show later, the synchronization to be improved. Okay, so one of the first experiments that we did now already quite a few years ago was at the European Expo. And so we brought our droplet injectors and we demonstrated that we indeed can obtain crystal structures from protein crystals injected in the droplets. So we obtained the room temperature structure of this enzyme, KDO8PS. This was in a non-synchronized mode. This was really just using our droplet injector, and we already got sample savings about 60% compared to a continuous GDVN injection. So this was promising, but we wanted to become better and reach these, larger than 90% sample savings that I mentioned earlier. So in the continuous injection, let me come back to how we are going to realize that. So again, related to continuous injection, we want to generate our droplets in our droplet generator. And in order to achieve synchronization now, what we do is we add electrodes here that allow us to use electrical stimulation to release the droplet. So Um, for that, we need then three major elements. One is our droplet generator, which, as I will show you later, can also be combined with a mixer for time resolved work. We need our droplet detector, as I just mentioned. It's not shown in this slide, but I'll show you realizations in a little bit. And then we need our nozzle. Okay. So here again is the schematics showing the fluidic channels in yellow, and then the electrodes very close by. We use 3D printing again to achieve this assembly and use a trick here. So we print empty channels very close, in very close proximity to the fluidic channels, and then fill these channels with conductive material so that we can bring these electrodes very close to the droplet generation region. The video shows, I think if it runs, it shows how the droplets are generated. This is without a stimulation. But then when we stimulate, what happens is the following. Okay, so again, in the middle here, you see a droplet release without stimulation. But when we actually stimulate or trigger, and we induce electrowetting effects that allow us to pin the droplets to the opposing wall, this is avoided under no stimulus because the capillary walls or the channel walls are treated in a way so that aqueous solutions do not wet it. But under triggering conditions, the sweating process is induced, and with that, we can actually tune the droplet release. Okay. Let's advance. Okay, here we go. Then this is showing the assembly of a so-called capillary coupled version with all three elements included. So we have a droplet generator that we can now electrically stimulate. The droplets are generated in this 3D printed piece and then connected to a capillary where they can flow downstream to the nozzle. And between the nozzle and the droplet generator, we integrate our droplet detector. It's basically the optical fibers that allow us to diagnose the differences in optical properties between the oil and the aqueous media. In the middle, you see a picture of the assembled device. Everything is very well protected in a lot of epoxy so that these devices survive vacuum insertion. But our first experiments then with these triggered or synchronized injectors has been at MFX. At the time at the Hera chamber when it still existed. So this is a picture where the whole assembly is inserted there. Okay, so with this slide, I want to show you that the concept actually works. So the video shows crystals that are injected if it starts running. Yes, that are injected in that way. What you can see in this video is this typical electrowetting effect when they're triggered. So this is all working out. And then in collaboration with Rick Kirian's group, we have developed a diagnosis system and a feedback system that allows us to see when actually synchronization and lock-in occurs. So if you don't have synchronization, then we see something like on the top here. Whereas when we have synchronization, then actually all droplets align very well in time. And I forgot to change the slide here. Actually, this is not 10 hertz because you see this is 8.3 milliseconds. So this is related to 120 hertz experiment and LCLS. So when everything works fine, all the droplets arrive in time at our droplet injector at the same delay to the reference exfil trigger. And that's the situation that we want to achieve for a synchronization experiment. Okay, so with these experiments at MFX, we could demonstrate that the feedback mechanism worked. We collected diffraction from 3 different proteins, and the resolution was, and the hit rates were comparable with GDBN injection. Okay, we also designed a different version of this to bring the droplet generation region closer to the GDVN. We call this the modular 3D printed device, or we also call it a Lego device, because we're basically putting three 3D printed pieces together like Lego pieces. You see we have these cups here and pins that we basically just stitch together. And the advantage of this is that we have the droplet generation region closer to the GDVN. It's one final piece. We have our droplet detector integrated here. And then potentially, as you will see later, we can couple this with mixers for time resolve work. We would also be able to achieve shorter time points with this assembly. So this is the modular droplet generator that we developed. We also tested it at MFX a few years ago, again in the HERA chamber. And here you see an image, a close-up of the inserted device in the HERA chamber. We were able to demonstrate that our feedback system works and our synchronization system works. So in order to achieve the maximum hit rates, we need to be able to tune the droplet release to a certain delay to the exfil trigger. And that's basically shown in the slide. So we can move the droplets around in the 8.3 millisecond window, and we can basically figure out at what delays we get the highest hit rates. So in this example, at about a 3 millisecond delay, we could demonstrate that we have the highest crystal hit rates. And so this would be the optimal condition for synchronization. We obtained structures of another enzyme, NQO1, and with a 2.2 angstrom resolution that was, again, comparable with the resolution obtained from a continuous GDVN injection. And then noteworthy to mention for this experiment is that it was the first SFX structure of that enzyme, and that we had a factor of 4 in sample savings overall from this experiment. Okay, so moving on. As I said, we wanted to make this droplet injector compatible with time-resolved experiments, and specifically with those that require the mixing of a substrate with a protein of interest. So what we did is, instead of just having one aqueous inlet, we added a second one that allows us to bring substrate in close proximity to our crystal solution, initiating mixing. And that mixing occurs by diffusion, but also due to the generation of the droplets, as I will show in a little bit. Okay. So we adapted this injector then to 10 hertz frequency at the European exfil, and it still has the major components. We have our electrodes included for the droplet stimulation. We have our droplet detector for the feedback, and then our nozzle that jets the droplets. And as I said, you can see up here that we have this additional inlet that allows us to bring the substrate in contact with the crystals. At the European exfil, we were fortunate that our collaborators also integrated this diagnostics into their data stream. And so that makes the whole experiment a little bit simpler for us. And this is how the nozzle looks like. There's a special adapter designed to bring it into the SPB SFX chamber. And then you see this is a version of the capillary coupled device as we would use it. And here's a nice picture of the droplets as they are actually imaged in the SPB SFX chamber. We have worked with the European exfil staff, even without our user beam time, to optimize the integration of everything in their system and to study our droplet injectors. Running them without crystals, as you can see here, we can run them for hours, stable, locked in, and we can do this phase shifting, as you see on the right-hand side. So we can, within a 100 millisecond window, we can easily move these droplets around so that we can obtain optimized synchronization. In our latest experiment, then we were able to successfully show the synchronization with this droplet generation approach. And on the top here, you now see these waterfall plots kind of turned around by 90 degrees. So you see when the droplets are locked in here, they're all nicely aligned. What this yellow color here means is that we also have crystal hits detected in that scenario. The times in between relate to setup and to change in parameters and optimization. So we can tune parameters, we get out of phase, and then we come back in and you see that we obtain a synchronization again. Good. Yeah, I wanted to say a few words about mixing and the time points that we achieved in that experiment. So this is a schematics of the droplet injector and the mixing portion. So basically here again, we see the two inlets in section A, the two liquids flow close to each other. So mixing is not very quick here, but as soon as the droplet is generated, you actually see that the vortices generated in the droplets facilitate mixing. So that's nicely shown in this video here. We were able to achieve or to measure time points time point of around 300 milliseconds and another of 1200 milliseconds in this experiment. And we determined through numerical modeling that we have a mixing time of about 5 milliseconds for the shorter time point, about 200 for the larger time point. Okay, so then the whole purpose of this experiment is to reduce the amount of sample consumed, and we could show that we only needed 3 milligrams for the 300 millisecond time point, and only and less than 2 milligrams for the 1200 millisecond time point, with a resolution of around 2.5 angstroms. And then the calculated sample consumption in comparison to continuous GDBN injection here for the longer time point is 97%. So we're reaching the goal in terms of sample conservation. A few words about NQ1. I saw that Jose is on the call as well. If you have more questions about the structural impact of this work, then I think he would be a very good person to ask. But basically, we're looking at the reduction of this lipo enzyme here on the right-hand side with NADH. And that was our substrate basically. And we noticed, binding of the NADH at the 300 and 1200 millisecond time points. And it actually, the data supported the distinct stages of NADH binding to the different NQ1 active sites. Okay, so this was a story about Xtel work with this droplet injector. And so we thought that, with the advances at synchrotron beamlines, we could also look into using these droplet injectors at synchrotrons. And so our first attempts were at ID29 at ESRF at the serial macromolecular crystallography beamline. So what we did for this was basically adapt our droplet injectors just in a way that makes it, in some sense, easier to use because we don't need the nozzle for the liquid injection. And so what you see here is the integration of our devices at the ID29 beamline. So they're very similar to use, except the GDBN. And so our droplets are generated in a similar way. We have the same feedback mechanism. And we just then needed to adapt a capillary to the outlet of the droplet generator that allowed us to detect inside. And you already see here two realizations. The very first one was with a glass capillary that we kind of just added to the outlet of the device. And then here we inserted a Kapton capillary and studied basically sample delivery in both these materials. Okay, so what's nice is if there's no chamber around, and you can actually look at things very, very nicely, very closely. And so this video here shows actually the droplets as they come out of the droplet generator. So we have a fused silica capillary to which we attach a quartz capillary, and you see these droplets nicely in there. I should say that the ID29 beamline can run at 230 hertz. And so we did synchronization approaches at 115 hertz because we had injectors that would work in that frequency, but we also attempted it later at the 230 hertz. What the other images here show that it's actually possible again to find synchronization and lock-in. And we obtained a structure from phycocyanin in quartz and kapton capillaries, as well as lysozyme in quartz capillaries. And let me go to the next one. Okay, so in addition, in our latest experiment, we also had proteinase K. So I show the fraction pattern here. And we were able to get a nice structure from phycocyanin and proteinase K from the latest attempts. So in order to comply with the higher repetition rate of 230 hertz, we looked at the functioning mechanism of this droplet generator and noticed that we can actually increase the droplet frequency by increasing the viscosity of the segmented phase or the oil phase. So we attempted this at home, basically with a higher viscosity and using more of the perfluorodecaline in our segmenting oil phase. And you see that we are able to generate droplets then at 230 hertz. And this is an at-home experiment with polystyrene bead included here. And we achieve lock-in. Notably, the really nice peak here at 230 hertz shows that this is possible. Okay, and it's a little bit hard to move on. Okay, so the second generation then included a mixing, include adding a mixer to the droplet generator, similar to what I've shown you in this European exfil experiment, in order to bring the mixing region between crystals and the substrate closer to where the droplets are generated, we changed the geometry a little bit. So previously, all the fluidic channels were on the same plane. But what we did here is we kept the oil channel and the crystal suspension channel on the same plane and now deliver the substrate solution from the top. So that's the beauty of 3D printing because that can be fairly easily realized. And with that, we calculated that we can achieve about a 50 millisecond time point under certain flow rate conditions. So it will always depend on the flow rate conditions that we need to achieve a certain frequency, what actual time point can be achieved. But we are well below 100 milliseconds with these mixers here. We also changed the approach of where we detect. So we put the capillary in which we detect the droplets connected it directly to the outlet of the droplet injector, and realized that with a Kapton capillary, that's a very tedious procedure to do. I admit if you do it by hand, so we used a Kapton capillary that was super thin, so very hair-like, but nonetheless, this is possible, so we could also attach it. And so you see here the whole assembly now realized with a just Kapton capillary. Okay, so this brings me to the end of my talk here. So I hope I could convince you that our droplet injector can be applied to a variety of injection scenarios, from 10 hertz at the European exfil to 230 hertz as at ESRF. We demonstrated the application for a variety of proteins. It's compatible with vacuum, air, or helium. We demonstrated sample waste reduction up to 97% at the European exfil. And we did apply the droplet injector to time-resolved experiments as well. So we have preliminary results for the segmented droplet injection at synchrotrons, and we have a capability for higher frequency. I think that's demonstrated through going already to 230 hertz, but I don't really see much of a limitation to go to up to a kilohertz or so with these injectors with some adaptations. And with that, I'd like to thank all the collaborators that are involved in these experiments. So quite a few generations of PhD students and postdocs that helped developing these devices, and then beamline scientists at the various beamlines, and then obviously our collaborators that are providing the protein to us, notably Jose's group in Madrid, with which we just worked last week again. And thank you for your attention.